तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
So today we shall begin our discussion on another logic family, that is the ECL, or the emitter-coupled logic, which is the fastest of all the logic families, and therefore has a important place in the family of logic families. Okay. So you have the emitter-coupled logic, or ECL. This is also sometimes denoted by another name called current mode logic, or CML. Okay. All right. So the basic structure of the emitter-coupled logic is like this. It is similar to the differential amplifier configuration in analog circuits. Okay. So you have a current source here, and you have the transistor, two transistors here. You can have more than them here. This side is grounded. This is a typical configuration. Okay. We shall come to that, why the circuit actually operates from a negative power supply. Okay. So here you have a negative power supply, and this is grounded here. So here you have a constant voltage at the base of this transistor, all right, and these are the inputs. Okay, say inputs A and B. All right, so this is the configuration of the ECL. Okay, now it is very clear why it is called the emitter-coupled logic, because as you can see, the emitters of all the transistors here are coupled together. All right. Okay, and the inputs here are at the bases of these transistors, and for this branch the input is a fixed voltage called the reference voltage, or VR. Okay. All right. Now, so how does this work, this logic work? So the output of the logic can be taken from the collectors of either of the two of this group of transistors here, or from the group of transistors there. So let me call this Y1 and let me call this Y2. Okay. All right. Now again, so you have a constant current source here, I naught. Okay. So the total current, total emitter current, all right, is constant, I naught. Okay. And now, so what happens is, now if A and B, the voltages, the input voltages are, these input voltages are much less compared to VR. Of course, one must remember here that we are operating with negative power supply voltages. Okay. So this is minus VEE and this is ground. So all the voltages in the circuit are negative. Okay. So, but it is a positive logic in the sense that if we will call it a logic high if it is, if the voltage is closer to ground. I mean, the more negative voltage is a logic low, all right. Okay, and the less negative voltage is a logic high. Okay. So, in fact, it is quite similar, you know, if you had a ground here and a plus VCC here, everything else is similar, but there is a definite reason for operating with negative power supply voltages, which I shall come to later on. Okay. So, when this input is less compared to VR, which means that when this input is more negative than VR, okay, then we can say that the base emitter voltage of this transistor is much less than this one. So, I will give them names, I think T1, T2 and T3. So, if VB, that is at the input B, is less than VR, okay, the base emitter drop of transistor T2 is going to be less than the base emitter voltage of transistor T3, okay, because the emitter point is common. So, if the base voltage is less, obviously base emitter voltage is less. Okay. Similarly, if VA is less than VR, the base emitter voltage of transistor T1 is less than the base emitter voltage of transistor T3. Okay. So, if the base emitter voltage of this and if these are they are usually identical transistors. Okay. So, if the base emitter voltage is less, it is quite natural that this is going to draw less current, okay, and it is the transistor with a higher base emitter voltage is going to draw more current. Okay. So, if VA and VB are both less than VR, okay, the majority of this current I naught. So, I shall call this, okay, let me call this IE 2 and this is okay, IE3. So, this is IE1. IE1 plus IE2 plus IE3 will be equal to I naught in this circuit, is not it? All the emitter currents, sum of all the emitter currents is equal to the total current. Okay. Now, if IE1 and IE2 is very much less than IE3, okay, then the entire current flows in this branch, the right hand side branch. Okay. All right. So, and there is very little current flowing in the left hand side branch. Okay. So, what is the so you have, so this is, let me call this R1 and let me call this R2, or let me keep it a constant resistance R in both the cases. Okay, it does not matter. Okay, R. Okay. So, what is the which so this, since IE3 is much more than IE1 and IE2, so the drop across this resistance in the right hand branch is going to be more compared to the drop in the left hand branch. So, what is the voltage Y2? It is going to be more negative compared to Y1. So, this is Y2 is logic low, where Y1 will be logic high. Okay. Is it clear? So, if both of them are low, both the inputs are low, Y2 is logic high, sorry, Y2 is logic low and Y1 is logic high. Okay. Now, if any one of them goes high, all right, if say VB becomes higher than VR, okay, so it is going to draw more current. Okay. And the, since again I1, so the left hand side branch, the total current flowing through this resistance is IE1 and IE2. If the beta of the transistor is high, we can assume that the collector current is almost the same as the emitter current. Okay. And so, the left hand branch draws more current. Okay. And so, Y1 will be low and Y2 will be high. Okay. All right. So, basically what is happening is by applying voltages, okay, low, if you apply high voltage at the input, you switch the current to the left hand side branch. If any of the input voltages go high compared to the reference voltage, all right, then the current is switched to the left hand side branch and the drop is less, and the drop across this resistance is higher, so that Y1 goes low. Okay. Whereas, if both the inputs are low, then the current is mostly in the right hand side branch and y2 becomes low. All right. So, what is the logic at y1? It is a NOR logic. Okay. Why is it a NOR logic? Because if any one input goes high, okay, there is a current flowing in this branch and this output is going to go low. Okay. And when this goes low, when y1 goes low, y2 is high. So, this is y1 is a OR logic. That is, when any one of the input goes high, because the current is flowing in the left hand side branch, there is no current in the right hand side branch, y2 is high. So, y2 is, so y1 is NOR of A and B, and y2 OR of A and B. Sorry, y2 is OR of A and B. Okay, y1 is NOR of A and B, and y2 is OR of A and B. Okay, is it clear? Now, so the basic idea is by you are switching the current in either of the two branches, okay, and the total current is constant, and if you apply an input voltage which is higher than the reference voltage, you have more current in the left hand side branch, okay, and that output voltage at here y1 goes low. Okay, and if both the inputs are low compared to Vr, okay, T3 is conducting, okay, T2 will be conducting, T2 and T1 is not conducting. So, y2 is going to go low, okay, and y1 is high. Now, so basically this is the operation of this ECL gate, okay, and you have these logics at the two outputs. Okay, now just to give you an idea of how much input variation is required to switch the current from one branch to the other. Okay. Now, just let us forget this, say T1 for the time being, okay, and say we have just one input here, T2, all right, and you have the other voltage, and you have T2 and T3. Okay. All right. Now, the input at the base of T3 is Vr, and the voltage at the base of T2 is Vb. Okay. Now, if you again recall the Ebers-Moll model which we had, okay, and just we neglect, we assume that the transistor is in the active region, that is base collector voltage is negative, all right, okay, it's reverse biased, and also beta is large. We can write that IE is almost equal to Is exponential VBE by VT. All right. So, IE2, okay, that is transistor T2, IE2 is equal to Is exponential VBE, for that is VB minus VE, if we call this emitter point voltage as VE, all right, the emitter point voltage here, common emitter point voltage as VE. So, VB minus VE by VT, all right. For transistor T3, IE3 is Is, okay, same Is, because as I said they are identical transistors. Is exponential, this is Vr, okay, minus VE by Vt. Okay, this is a common emitter voltage. So, Vr minus VE by Vt. So, IE2 by IE3 is equal to exponential Vb minus Vr by Vt. All right. Okay. So, now we can write, next step we can write Vb is equal to Vr plus Vt ln IE2 all right. Okay. All right. Now, so this is the relation governing the input voltage and the two current and the emitter and the two emitter currents. Okay, VB is the base voltage for transistor T2 and VR is actually the base voltage transistor T3. Okay. Now, with this relation we can now see very well that if IE2 say is equal to 95% of I naught, that is the total current, okay, then what is this VB equal to? VB will be equal to VR plus VT ln, this is 95%, so IE3 is just 5%, so 95 by 5, so VT ln 19, all right. So this is ln 19 is around 3, okay. So this one is going to be, and this is around 25 millivolts, so this is VR plus approximately 75 millivolts. Okay. So the point here is that if the base voltage at the if the input voltage at the base of T2 exceeds VR by just 75 millivolts, then the 95% of the total current flows in transistor T2. That means almost the entire current flows in transistor T2. Okay. All right. So we put 95% because you cannot put 100%. Okay, it is, that's the problem. Anyway, if IE2 is say 5% of I naught, VB is equal to VR minus VT ln 19, same thing, 5 by 95. So VR minus 75 millivolts. Okay. So you see that if VB is less than VR by just 75 millivolts, it's almost carrying no current. Okay, the entire current is flowing from to the other branch. Okay. All right. Whereas if you exceed VR by 75 millivolts, you get the entire current flows in the branch. So you can switch the current in this circuit from one branch to the other, okay, almost the entire current, by changing the input voltage by just about 150 millivolts. Is it clear? So from VR minus 75 millivolts, when entire current flows in the right hand side branch, if you exceed it, make it VR plus 75 millivolts, the entire current flows in this branch. So you see, the important thing here is you require just a very small voltage variation, okay, to change the state of the logic, okay, which is very important here because that gives us very high speed, all right, okay, and that is a direct result of the exponential the dependence of current with voltage. Okay, in MOS circuits you would require a large voltage variation, okay, to change the logic. Okay, here you require a very small voltage variation to change the logic, and small voltage variation requires less time, so you get high speed. All right. So all these things are related. So if I just plot it, you know, if this is the reference voltage, okay, and I plot V in, or I call VB, all right. So and if this is say VR minus 75 millivolts and this is VR plus 75 millivolts, okay. So here when it is VR minus 75, see, just the current is switching from one branch to the other. So when VR minus 75 millivolts, so this is I naught, okay, this is I naught here. So when it is VR minus 75 millivolts, when VB, so IE2 is only 5%, so IE3, so this is IE3, this is IE3, this is IE2. Okay, this curve is IE2, this is IE3. So you see that when VR minus 75 millivolts, IE3 constitutes the entire current. Okay, whereas IE2 is very small current. Of course, when VB is equal to VR, okay, then both of them should carry the same current because they are all identical. Okay, there is no there is absolute symmetry. Okay, and when VB becomes VR plus 75 millivolts, okay, IE2 is going to carry almost the entire current, while IE3 goes to is carrying negligible current. Okay, so by a small change in input voltage, you are able to switch the current from one branch to the other. Okay, all right, and when you switch the current from one branch to the other, the drop in these two resistances, the two branches, changes. Okay, so when one was carrying the entire current, the output voltage here, when the left hand branch carries the entire current, Y1 would be low. Okay, Y2 will be high. When the right hand side carries the entire current, Y2 will be low, Y1 will be high. So you are able to change the state. Okay, and here you are having two transistors in parallel, which means that if any of them is conducting, okay, the left hand branch is going to carry is going to carry the current. All right, so you can have more than two. I mean, you can have 3, 4 in parallel. Okay, you want a 3 input NOR gate, you have 3 transistors in parallel. You want a 4 input NOR gate, you have 4 transistors in parallel. Okay, so this is how ECL works. Right? Okay. All right. So we have seen that how the circuit works. Okay, there is no problem. But being a high-speed circuit, it has to have certain important considerations. That is, these transistors are supposed to work in the active region. Okay, they are not. They should not go to saturation, because if they go to saturation, then you have the delay related problems. Okay, so in fact, these transistors switch between the cutoff and the active region. They do not really go to saturation. Okay, now how do you prevent this transistor from going to saturation? In this particular circuit, the transistor is prevented from going to saturation by choosing the values of I0, R, and the input voltages appropriately. Okay? So if you choose these values appropriately, you can ensure that this transistor does not go to saturation. Okay? Now how do you do that? Now we shall take up that next. Okay. Now let us suppose that we choose, I mean, I am just saying like this, that let us suppose that we choose I0 and R in such a way. I0 is the current source and R is the collector resistance. Okay, that the product I0 into R is equal to V on, okay, where V on is the base emitter voltage of a conducting transistor. Okay, when the transistor is conducting, the base emitter voltage is V on. Okay, that is around 0.7 volts. 0.7 in some cases in ECL, because these transistors are very small, this V on may be 0.8 volts also. Okay, so 0.7 to 0.8 volts. All right. Now let us choose I0 into R in such a way that I0 into R, I0 and R in such a way that I0 into R is V on. That is, we have chosen this. Okay. So if this is how we have chosen, okay, then we can say that the minimum value that can, the minimum voltage that we can have at the collector of a transistor is what? Minus V on, okay, because the maximum current that can flow through this resistance is I0, okay, in a branch is I naught, and so the maximum drop that you can have is I naught into R. So you cannot have a collector voltage which is less than minus I naught into R, okay, all right. So if I naught into R is V on, we can say that Vc min is equal to minus V on, all right, because I naught into R is V on, okay. So this is one thing we have seen, all right. The next condition which we impose is that let Vi, okay, this is the input voltages, Vi we call the input voltages, okay, is equal to Vr plus minus half V on. That is, the input voltage variation has to be it is half, it is a range of V on about Vr, okay. That is, the input voltage can vary from Vr minus half V on to Vr plus half V on, okay. That is, the input voltages at the inputs, okay, they should vary within this range. If we ensure that, okay, we want to ensure that, okay, it should not exceed that variation, okay. That is, the total input variation will be 1 V on, okay, from Vr minus half V on to Vr plus half V on, okay, all right. Now, if we have this condition, okay, what is Ve max? That is, we have seen Vc min, okay. Now, what is Ve max? That is the maximum value voltage that we can have at Ve. That is going to occur when the input voltage is at its maximum, okay. When this input voltage goes to the maximum, okay, that input voltage minus V on is going to be the maximum value you can have at the emitter point, all right. Okay. So the maximum value you can have at the input is Vr plus half V on, okay. So if this is Vr plus half V on, the drop across the base emitter drop is V on. So Ve maximum is going to be Vr minus V on, okay. So Vr plus half V on minus V on, okay. So this is Vr minus half V on, okay, all right, clear. Now, so what is Vce minimum? That is, the minimum collector emitter drop which you can have is obviously Vc min minus Ve max, okay. When the collector voltage is at the minimum, emitter voltage is at the maximum, that is the minimum value of the collector to emitter drop which you can have, all right. So this is Vc min minus Ve max, all right. So what is this equal to? Minus V on minus Vr minus half V on, all right. So this is equal to minus Vr and plus half V on, so minus half V on, okay, all right. So this is the Vce min, all right. Now we can prevent the transistor from going to saturation by limiting the value of Vce min, okay. We know that if the transistor, when the transistor starts conducting more and more, what is happening is the collector voltage is dropping, okay, and the Vce is going to reduce. Now as the Vce reduces, okay, the transistor starts going to saturation, the collector base junction starts getting forward biased, is it not? So because base emitter you have say 0.7 volts, so when Vce is 0.7 volts, collector base junction voltage is 0. If Vc falls below 0.7 volts, it means that the base collector junction is getting forward biased. Okay. So, we can prevent the transistor from going to saturation by limiting this Vce min. Okay. Now, say we limit it to V on. Okay. That is, we will not allow this Vce min to go below V on. Vce min is equal to V on. Okay. If we limit this to V on, we effectively prevent the transistor from going to saturation. Okay. Now, suppose we put this equal to V on, all right. So, Vce min is equal to V on. Okay. So, what do we get? We get the third condition, okay, that is Vr equal to minus 3/2 V on. I will write it here. Okay. So, these are the three conditions which we have, all right. One is, if we choose I naught into R is equal to V on, we choose the current source value and the resistance values in such a way that their product is equal to V on. Okay. If we ensure that the input voltage variation is just V on, okay, around Vr, that is from Vr minus half V on to Vr plus half V on, and if we choose Vr is equal to minus 3/2 V on, we will ensure that Vce min is V on, that is the minimum value of the collector emitter voltage is V on, and which effectively ensures that the transistor does not go to saturation. All right. So, collector emitter drop will always be greater than V on. Okay. So, this is the design principle. Of course, it is very clear now that if Vr is minus 3/2 V on, okay, the input voltage variation is how much? Minus V on to minus twice V on. Okay. All right. So, these are the design principles. Now, if we come back to this circuit again, okay, what so this is a OR NOR gate. Okay. This is, you have both OR and NOR outputs. Okay. And this output is to be fed as input to another gate. Okay. So, there is some problem which we see right away. Okay. We expect the input voltage to vary from minus V on to minus twice V on, all right, okay, because that is how we have designed it. Vr is minus 3/2 V on, V input should be Vr minus Vr plus minus half V on. So, it should be from minus V on to minus twice V on. But what is the output voltage here? Output voltage is going to change from, so if say if you take the output from Y2, okay, when no current is flowing in this branch, the output is equal to 0. Okay, the voltage here is 0, it is ground voltage. Okay, and when the entire I naught is flowing in this branch, the voltage is minus V on. So, the output voltage at any output is varying from 0 to minus V on. Okay, whereas the input, we require the input to change from minus V on to minus twice V on. Okay. So, that is one anomaly we have, okay, which has to be solved, okay, for this circuit. The other problem in this circuit is that, okay, what happens is if you feed this output to the input of a next gate, say, okay, and there is a current source here, just drawing it here. Okay. So, this output is going to the input of the next stage, all right. What happens is this is I naught. So, when this branch is not conducting, okay, this output should be 0, okay, the voltage here should be 0, all right. But what happens is this transistor, the input is logic high for this, isn't it, when this output voltage is 0. So, this transistor is going to conduct. Okay. When this transistor is going to conduct, there is a base current which is going to flow, okay, which is going to be equal to I naught by beta. Okay. I mean I naught by beta plus 1, but okay, it is almost I naught by beta times. current which flows here, and where is this current going to flow? Through this resistance. Okay, it actually flows through this resistance into the base. Okay. So what you are having is a current flow through this resistance, and so what happens to this voltage here? Because of this current flowing here, this voltage is going to reduce. Okay. So if you have a large number of fan outs, I mean all this output here is logic high here, isn't it? So all the current which will flow through this resistance, through all the fan outs. Okay. You have all these fan outs, so all these transistors will be conducting. So this total current here through this resistance, okay, is going to be how much? I naught divided by beta times n, where n is the number of fan outs. So this much current flows in through this resistance, and so in times r is going to be the drop across this resistance. So the logic high is going to fall. Okay, there is going to be a drop in the logic high, okay, and which may give rise to problems because the logic swing here is very small. Okay, that is deliberately done, as you know, for high speed circuits. All right. So these are the two problems we have. One is the input and output voltages are not matching. Okay. The second problem is that if you have a large number of fan outs, okay, you may have problems because the logic high voltage is going to fall, and the difference in voltage between the logic high and the logic low is going to get reduced. Okay? Clear? So how do you solve this problem? Well, there is a very simple solution. What is done is, in this circuit, the output here is taken through emitter followers. Okay, so you have an emitter follower here, and the output is taken from this point. So here also, this output also, all right, you have another emitter follower. So these are the two outputs now. Okay. So for the two outputs here, now they are taken through emitter followers. Now what does the emitter follower do? How does it? It solves both the problems. Okay. So here now, what is the output voltage variation? It is basically shifting the output voltage by V on. Okay. Now when this voltage at the base of this emitter follower transistor is 0, the output is going to be minus V on, and when it is minus V on here, it is going to be minus twice V on. All right. So it's basically shifting the voltage down by V on. Okay. So the output voltage variation now is going to be from minus V on to minus twice V on. Okay. And that is what is our requirement for this ECL gate. Okay. We have seen Vi should be Vr plus minus half V on. Okay. And if Vr is minus 3/2 V on, the input voltage should vary from minus V on to minus twice V on. All right. So you see that this effectively solves our problem number 1. Okay. Number 2, the second problem. Okay. The second problem is about having a large number of fan outs. Okay. There is going to be a voltage drop in the resistance. Now in this circuit, if you are connecting the fan out here, the output here, okay, again you have a current I naught here. So this voltage Y2 is logic high, say. So this transistor, the next stage, is going to conduct. Okay. So if this is I naught, the base current is I naught by beta. Okay. And what is the current on the base here? Because this is there is I naught by beta, but plus a small current, Okay, this is usually a high resistance, so this current is much smaller. So again, we can, if you neglect the current flowing through this resistance, so the current flowing here is I naught, this base current here is I naught by beta squared. So the drop across this resistance, okay, drop across this resistance here has been reduced by a factor beta. All right. So previously the current which was flowing through this resistance was I naught by beta times n. Now it is I naught by beta squared times n. All right. So when beta is quite large, this resistance, the drop across this resistance can be reduced. So you see that using an emitter follower at the output, okay, we have been able to solve both these problems. Okay. So now we can see that this circuit is, firstly we have seen that this circuit is going to behave as an OR and NOR gate, okay, and only a small input variation around the VR, which is the reference voltage, okay, is sufficient to switch the current from one branch to the other. Okay. And as the current switches from one branch to the other, the output voltage changes, okay, from one logic to the other. And also we have seen the condition to ensure that these transistors do not go to saturation. Okay. So we have to ensure this condition while designing the circuit. Okay. The three conditions: I naught into R is V on, Vi must vary from VR plus VR minus half V on to VR plus half V on, and VR should be minus 3 by 2 V on. Okay. And if you have an emitter follower, the output voltage is going to satisfy the requirements of the input voltage, that is, the output can be fed directly, okay, to the input of the next stage. Okay. All right. And also here there was a small problem related to if you had a large number of fan outs, okay, because the voltage level itself would change, but this could be reduced by having the emitter follower. So this, from this point of view, the circuit is okay. All right. So there is one small point, one more point which I think is in the back of your mind, why we are using negative power supply voltages. Okay. The circuit would work perfectly all right, the circuit would be perfectly okay if this was ground here instead of minus VE and you had a VCC. Okay. There would be no difference in the operation of the circuit. Okay. But why we are using a negative power supply? Well, I'll just discuss that now before we close today. Yeah. See, the ECL gate, like all high speed gates, we have already discussed that. There is some problem due to noise. Okay. All high speed gates suffer problems due to noise because of the very fast switching. Okay. And large amounts of currents are switched from one branch to the other. Okay. And because there are some inductances in the circuit which normally you tend to neglect, and you know, if you have a if your current is changing, dIdt is very fast, you know, is very high, you know. So and if there is an inductance, you get certain voltages. All right. L dIdt is the voltage. Okay. Now all this gives rise to what is called power supply noise. Okay. That the power supply, the voltage should be a constant, but across the power supply you get some noise when the switching takes place. All right. Because of these interconnections and all, they are not perfect. All right. They have certain inductances and all. Okay. So all these high speed circuits, because of the fast switching which takes place, give rise to certain noise across the power supply. The power supply voltages are not dead fixed. Okay. And these this noise should not affect the operation of the circuit. All right. Now if you take the output now, if you look at the output of this circuit now, okay, usually I will just put some representative values. This resistance, which is the emitter follower, is around 1.5 kilo ohms, whereas this resistance is around 300 ohms. Okay, that is the resistance at the collector. Okay, this is around 300 ohms. Okay. Now, if you assume a voltage noise source across the power supply, okay, just take this circuit and you have a 300 ohms here resistance, then you have the emitter follower output like this, and you are taking the output here. This is 300 ohms, this is 1.5 kilo ohms. Okay. All right. Now, there are two options. Either you take the output voltage across this, okay, say let us call it VO1, or you take the output voltage across this VO2. All right. Okay. Now, what is the effective resistance seen from this point? Okay, this is going to be this 300 ohms divided by beta. Okay. So, this resistance, effective resistance, okay, across these 2 points, all right, is 300 ohms divided by beta. All right. Now, if the beta is say about 100 for this transistor, so the effective resistance would be 300 by 100, which is around 3 ohms. Okay. So, this the resistance from this emitter point to the top here is around 3 ohms, whereas this is around 1.5 kilo ohms. Okay. And if you have a voltage source like this, okay, this one would be almost equal to Vn, and this one will almost be equal to 0. All right. Okay. So, this is the output. Either you take the output across these 2 points, or you take the output across these 2 points. Now, so you see that if you take the output across the lower 2 points, okay, the full effect of noise would be felt at the output, whereas if you take the output between the 2 upper points, the effect of noise is virtually eliminated. All right. Okay. So, it is advantageous to take the output between the upper 2 points, and you see in any circuit the ground is always the reference point, okay, across with respect to which you take the output. All right. So, what is advantageous is to make this ground and put a negative power supply rather than putting this as VCC and this ground, in which case you are taking the output, basically taking the output across these 2 points. All right. Okay. So, that is one reason why it is advantageous to put have the upper point this voltage here as ground and this as negative minus VEE. All right. The other reason is, you see in any circuit, as I said, the ground is the reference point, and if you are housing the equipment in a box or something, no, you usually make that the ground, okay, you earth it. All right. And there is always a possibility that the output of the circuit, okay, is getting coming in contact with the ground, all right, or the reference voltage. Okay, that is by mistake also the output you can touch, the output can touch the ground. If you are taking a wire, it can, okay, it can get shorted to the ground. All right. Now, if this was ground and you had a VCC here, okay. Now, if this output is shorted to ground accidentally, what are you having? This transistor, okay, the entire VCC comes across this transistor and there is no resistance to limit the current. Okay. So, a very large current is going to flow through the resistance and is going to destroy the transistor. On the other hand, if this is minus VEE and this is, and the upper part is ground, okay, if this point gets touched to the ground, okay, there is effectively no problem because you are just having, there is no voltage across this device. All right. So, the output point touches ground, okay, no problem. So, there is a short circuit protection as such inherently built in the circuit, which is not there when if you take the output across this point, okay, and this point is the, and you have a positive power supply with the ground here. Okay. So, these are the reasons why ECL traditionally uses a negative power supply, okay, and that is why it is different also from the other logic families. Okay. So, we stop here today, and we shall continue our discussion in the next class.